Today, we are diving into a really fascinating and honestly pretty radical geometric theory of physics. It's one that tries to unify some of the most fundamental ideas we have about how the universe works. So let's start with the big question, the one that really kicks this whole thing off. What if the most famous equations in physics, the ones you learn about in textbooks, aren't truly independent from one another? What if they're all just different faces of a single, much deeper underlying structure? Well, that is exactly what the Methane Metauniverse theory, or MMU, suggests. You see, standard physics treats these ideas as separate pillars of our understanding. But this theory, it proposes there's a single geometric foundation for all of them. For the Balmer spectrum of atoms, for the quantum waves in the Schrödinger equation, for the spin in the Dirac equation, and yeah, even for Einstein's gravity. So how in the world does it do that? Okay, let's get into the core idea of the MMU, starting with its most fundamental building block. First off, in this model, spacetime isn't the smooth, continuous thing we usually imagine. Instead, it's described as a discrete lattice. Think of it like a crystal, built from individual, countable units. And these fundamental units are called cells. Now, each one of these little cells has three hidden internal properties, or what the theory calls channels. You've got W2, which is the electric channel, W3, the torsional or spin-related channel, and W4, the volumetric or gravitational channel. This is basically the secret internal life of space-time itself. And right here, this is maybe the most crucial rule of the whole theory. It's called the projection principle. Basically, those internal coordinates, W2, W3, and W4, we can't actually see them directly. It's kind of like a shadow. The rich, three-dimensional movement of an object gets projected as a simple, flat shadow on the wall. Well, in the same way, the physics we actually see and measure is just a projection, a shadow of these hidden dynamics onto an observable axis called W1. And this leads to a pretty wild idea. It means that even time itself isn't fundamental. Instead, time emerges from the system. It's a projection of those hidden internal dynamics, just like the formula here shows. All right, so if all these different pieces of physics are supposed to pop out of the same place, there's got to be a common starting point, right? So let's take a look at the master equation that's running the show in this hidden world. The central idea here is that MMU doesn't start with a bunch of separate laws. It starts with one shared, hidden dynamic. You can picture each cell behaving like a tiny system of coupled oscillators, kind of like a set of masses all connected by vibrating springs. And all that hidden wiggling and jiggling is governed by a single master equation. It describes how the cell oscillates, where that K represents its stiffness. But here's the kicker. The stiffness isn't constant. It actually changes based on the cell's size, and it follows a universal scaling rule. So you've got one geometry, one internal dynamic, and from that, you can get a whole bunch of different observable results. Okay, so let's follow the first path and see how this whole framework could actually give us something we recognize from experiments, like the light spectrum from an atom. In the MMU, stable things like an electron in an atom can only exist when the internal oscillations close in on themselves perfectly. As the equation here shows, the phase shifts of those hidden channels have to add up to a complete circle, or a multiple of one. This is the phase closure condition. And this phase closure condition is everything. It's what forces the system into discrete allowed states. You can't just have any old value. When you combine that with the scaling law for the cell's elasticity, you end up with a length that grows like n squared. And when you project that to see what the energy looks like, it falls off as 1 over n squared. And just like that, the theory says you get the famous Balmer structure of the hydrogen atom emergent from the geometry. Now for path number 2. If the universe is built on this discrete, crystal-like lattice, then where do the smooth waves of quantum mechanics come from? Well, according to this theory, the Schrödinger equation pops out when one of the cell's internal vibrations starts to dominate everything else. You can imagine one string on a guitar vibrating way more powerfully than the others, and that one note defines the sound you hear. So when that happens, you can separate the super-fast microscopic jiggling from a much slower, smoothly changing envelope that rides on top of it. And if you zoom out, in the long wavelength limit, that slow envelope behaves exactly like a Schrödinger-type wave. So here's the big takeaway. In this view, the wave mechanics we all know and love is still totally valid, but its role is different. It's not the fundamental starting point anymore. It's an emergent property of a deeper reality. Okay, on to our third and, maybe the most profound path. How does this geometric setup explain the weird quantum property of spin in the famous Dirac equation? This is where that W3 channel, the torsional one, really steps into the spotlight. The idea is that this channel is special. It has a unique two-state structure, and that is supposedly the geometric root of spin. You can literally think of it as two opposite kinds of twists, a left-handed twist and a right-handed one. And this simple geometric feature is proposed to be the origin of spin 1/2, which is, a fundamental property of all the particles that make up matter. So under certain energy conditions, the whole dynamic of the Orr cell gets dominated by just these two torsional states. And from that simple two-state system, a specific type of mathematical operator just naturally appears. When that structure then couples with another mode, the claim is the full Dirac equation, the one that governs relativistic electrons, just emerges. So in the methane metauniverse, really fundamental things like spin or the way spinors behave, or even the existence of antimatter, they aren't just baked in as starting assumptions. They're interpreted as direct consequences of the underlying geometry of spacetime. And that leaves us with a pretty provocative question to chew on. Could the incredible, rich complexity of our universe really, truly emerge from the simple rules that govern a single repeating geometric shape? That's the challenge this theory puts on the table.